Well, and welcome back. So, okay, so when people talk about how to damp out longitudinal phugoid motion, when we talked about in previous videos, we talked about aircraft approaching the sound barrier, okay, and approaching critical Mach, and getting this oscillation going on, which was the shock wave destroys a bit of lift, alters the centre of gravity, which alters the balance and trim of the aircraft, which can bring the nose up. Another thing that can happen is the shock wave can also bring the nose down. It can alter the balance of the aircraft, so the nose goes down, it goes faster, creates a larger shock wave, which then moves the centre pressure forwards, right, which then brings the nose up. So different aircraft designs can make Mach, and this is called Mach tuck. Okay. The other thing that can happen with a standard aircraft, with the tail, right, if you get a shock wave on the tail or you get separated flow, I'll show you that with the Spitfire. So if you get separated flow from the wing hitting the tail, it can cause tail buffeting, which is why we have delta wings. It can also cause a loss of downforce on the tail, which causes the aircraft to go down slightly, which speeds it up, okay, which as it speeds up it creates more lift on the wing, yeah, which makes it sort of like go nose down, speed up, and then come nose up again. And it can cause this kind of like this oscillation. There's various things depending on the aircraft design that can happen, but the probably quite a common one is that the centre of pressure moves forward, it lifts the nose up a little bit, it increases the angle of attack, which increases the drag, which slows it down, which makes the shock wave disappear, which drops the nose again. So you get this kind of shock wave, no shock wave, shock wave, no shock wave, shock wave, no shock wave. How do most aircraft get around it? They have two big massive afterburners at the back if they're supersonic aircraft, and they go, oh, we don't like this wobbly bit, let's go faster. Once the aircraft is in full supersonic flow and the shock wave is at the back of the aerofoil, here, attached to the back of the airfoil, this whole wing is in smooth laminar flow in the supersonic condition, and your stability problems have largely gone away. You're back to normal balance and things like that. The aircraft that struggled with this was the generation just after the Spitfire. Okay, so your first jets, your Gloucester Meteors, your Supermarine Swifts, your F-102 Delta Darts and F-106 Delta Daggers. I always get them two mixed up the wrong way around. One's a Delta Dart, one's a Delta Dagger. I think it was the Dagger was the first one. Your F-106 is the first time. Your F-104 Starfighters, your Hawker Hunters, lots of aircraft struggled a little bit. The Blackburn Buccaneer had it nailed. Okay, Blackburn Buccaneer, swept back wings, vortex generators, a high T-tail, an all-flying tail plane. Actually, the Buccaneer has a thing where somebody will probably correct us on this. I think the Buccaneer goes into two modes. It has an all-flying tail, and then if it goes into takeoff and landing, the tail stays where it is, and the back moves like an elevator. But I think at high speed flight it moves to an all-flying tail. I don't know, I'll have to check on that. Anyway, right. What else do we have? Obviously British aircraft. Delta wings on the Vulcan and the Javelin. You know, all these aircraft solved this problem. More modern about shock waves appearing on thick part of the wings and causing shock wave type and separated flow type problems. Right, now your wobble, your early Gloucester Meteors, okay, and some of the fast Spitfires, some of the really fast Mark 21 Spitfires that were approaching the sound barrier in a dive, okay. The problem that they had was the shock wave would turn up and cause an imbalance. It would cause this Mach tuck thing to go up, and the aircraft would oscillate up and down quite rapidly. Okay, this rapid oscillation. What we get now, right? Aircraft that are designed to fly at high transonic speeds can suffer from something called longitudinal phugoid instability. And a phugoid is just an oscillation. So an oscillation like this, like a sine wave type of thing, up and down, up and down, up and down of that magnitude, right? If we then massively increase the wavelength of that, so we have this going on. So it's an oscillation like that, right? That you can barely, I've drawn that so you can see it. Sorry, I've drawn that too low. Keep forgetting I'm off the board. Yeah, so a phugoid is an oscillation like that, and that's actually going up and down a bit, and you can barely see You know, you can barely detect the up and down motion of it. It is going up and down, and it is repeating just like the sine wave on top of there, but it's an incredibly long wavelength of oscillation. Okay, they can oscillate up and down a fair bit, you know, so it could be like a, you know, if you zoomed in on that, if you saw something like that, yeah, that could be the top end of a phugoid, yeah. Right. Anyway, what causes them? You got your standard wings, okay? You got a standard wing, you got a standard aerofoil. If that shock wave appears, right, like there, and it's a very small shock wave, right, you'll get the same thing happening as the thing I showed you earlier on. You'll get this slight alteration of the centre of pressure, which will slightly raise the nose, and we're talking very slightly, which will very slightly and very gradually slow the aeroplane down. As the aeroplane slows down, the shock wave will very slightly and very gradually disappear. Okay, and it'll go and very, very slightly and very gradually go back to level flight, where it will accelerate again very slightly and very gradually. This is aircraft that are at the top end of the performance module, so they are at the top end of the performance. They have subsonic engines and they're flying about Mach 0.9. So this is a phenomenon. We're talking modern airliners that are flying very, very close to the speed of sound without actually going supersonic. Okay, so very Mach 0.9, tiny little increase in angle of attack. Okay, slows the aircraft down a little bit. Okay, the shock wave, because the shock wave is created by speed at the critical Mach, it takes it below critical Mach. The shock wave disappears. Okay, which means the centre of pressure goes back rearwards again, which drops the nose slightly back to the original thing. And then because the thrust is still there, okay, the thrust is still there behind the aircraft, it pushes the aircraft forward again. Yeah, speed builds up over time. Very, very slow acceleration, angle of attack goes up and it slows down, so you get this sort of thing going on, right? Now what happens is, when the angle of attack goes up, the aircraft will rise in altitude and it will fall, and as the angle of attack, as the shock wave disappears, it will go back to its original trim and the aircraft will fall in altitude until it accelerates. So the aircraft will be very slowly, over a massive distance, hundreds and hundreds of miles, the aircraft will be doing that. Just up and down like that. Okay? Now, it's a waste of fuel. It's energy. Every time it increases that angle of attack, it burns a little bit more fuel. Okay? When it accelerates needlessly, okay, it doesn't get the benefit of that acceleration and that extra fuel economy because it wastes it by the angle of attack going up and slowing the aircraft down. So this slowing down of the aircraft causes a problem. What we want is no shock wave. Right? Or what we want is a very small shock wave, or a very small, very weak shock wave, as far back on the wing as possible. So, I didn't cover this in class before. Well, look at critical Mach numbers. What you want is a very, 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 very high critical Mach number. Okay, critical Mach number as close to 1 as you can get. Okay, that means your transonic phase. So for a poorly designed aircraft, right, where the shock wave turns up, it's a curvy wing. If you put afterburners on an A10 tank buster, you'd end up with a shock wave this big because it's got a very, very curvy wing. Okay, so what I don't want is a big massive shock wave messing up all the lift, messing up all the balance and knacking things up. Right, so what you want is, you want the transonic region of, yeah, your shock wave turns up, it's tiny and it only turns up at Mach 0.99 or Mach point, let's be realistic, Mach 0.97. Right, and then your shock wave goes away and your shock wave is back here and not bothering anymore at Mach 1. Okay, if you've got a poorly designed aircraft, you could have it, that aircraft's transonic range. Its critical Mach number is 0.97, its full supersonic range is Mach 1. Brilliant. Some aircraft have a critical Mach at 0.7 and then they're not fully supersonic until Mach 1.2. Okay, that means from Mach 0.7, yeah, about maybe 500 miles an hour or whatever, up until 700 miles an hour, that 200 mile an hour acceleration bit where they're suffering all this sort of stuff going on. Yeah, so that is a poorly designed aircraft for going high, for efficiency. Okay, because you're in that transonic range. You want to be in the transonic range for as small a time as possible. Yeah, so easy way, big massive afterburners, yeah, loads of thrust. You can push a brick through the sound barrier if you've got enough thrust. It's all about thrust. Loads of thrust, yeah, away you go. Problem solved. Problem with that is, with the afterburners on, you're chucking fuel out the back of the aircraft, not very fuel efficient, killing lots of polar bears. No one's happy with that. Okay. Even Donald Trump, who probably doesn't care about polar bears, it's costing him lots of money to fly his aeroplanes, so he's still not happy. Right. Right. What we can do is have a thing called a supercritical wing. Standard wing, shockwave forms here, gets bigger, yeah, gets smaller as it goes back, goes to the back of the wing. Supercritical wings, lost me black pen. Or like this. They have a very flat section on the top of the wing, and then they'll have a section like that, and actually they'll probably be like that sort of shape there. They'll have like a blunt trailing edge as well for some reason. Now I'm not going to go into exactly why these supercritical wings are designed like that. What you can remember is that they work more effectively, supercritical wings. If you think, well, that's flat on the top, how is that going to create lift? Your angle of attack on the supercritical wing when it's landing and taking off will be slightly higher than a standard aerofoil. Okay, so you have to look at it from that kind of, I should have drawn it on a slight angle really. Okay, but when you trim the aircraft and you want to fly fast at high transonic speeds with a supercritical designed aerofoil, right, because the faster you go, one of the 5 factors affecting lift is velocity. The faster you go, right, the less camber you need, the less surface area you need, because the speed makes up with lift. Because you're going faster, right, the speed makes up for the loss of lift because you're not as cambered, or you're not as, or the angle of attack's less. So you can reduce, the faster you go to fly at the same lift, you can reduce your angle of attack if you increase your speed. So if we reduce our angle of attack, you've got a little bit of a curve on the top. You've got this curved section at the bottom. So from this point of view, right, the aircraft has a sticky out bit at the top. It produces all of its lift here, right, but it accelerates the air very quickly, but also very, very gradually. Okay, there's no bump for that shockwave to form on. There is no point of maximum camber where the shockwave can say, oh, I'm going to form there and I'm going to stay there. Okay? So the point of maximum camber, it kind of does away with it. And remember, lift's caused by a difference in pressure above and below the wing. So this cutaway here also affects the pressure variations on the wing, and it forms a smaller and weaker shockwave a lot further back. Standard wing shockwave would form about here. A supercritical wing. Supercritical means it can fly at a high critical Mach number, or it can fly at a high Mach number before the shockwave forms. So it's supercritical. So that means that the shockwave will form a lot further back and a lot smaller than a standard wing. And as well as this downturn at the back means when the shockwave moves back down here, it means that the turbulent air, because of this effect on the bottom of the wing, right, it cuts down. You still get, on supercritical ones, you still get separated flow. You're still going to get a bit of separated flow there, but it cuts it down a little bit because it's a very gradual curve. Okay? And it takes a little bit of energy out of this downturning bit here and keeps that a bit more laminar at the back. I'm not going to wax lyrical on that because I haven't done enough research on exactly what happens on the back end of there, right? But I know that most of them have this kind of downturn at the back. The main thing about supercritical wings, smaller and weaker shockwave, okay, which means that your longitudinal phugoid motion, which is caused by the shockwave appearing and disappearing, okay, with a supercritical wing, if it does appear, it appears, it stays there. It doesn't, because of the how far back on the wing it appears, it doesn't affect the longitudinal trim of the aircraft that much, so it stops this phugoid getting any worse, or it stops this. It doesn't stop the phugoid. Well, in some instances, you may still get a phugoid, but it damps it out. It makes the phugoid less prone. There's less of an oscillation on it. Okay, it doesn't go up and down as much. It might just go up and down that bit. Okay, so it damps out the phugoid until it's basically non-existent. That's my theory anyway. If I was asked to put an answer on an exam, how do you damp out longitudinal phugoid motion on high transonic speed aircraft, that's what I would say. Okay, if that's the wrong answer, then please, I'm sure lots of pilots, everybody starts talking about yaw dampers, please, that's a completely different plane of motion, right? If there's any avionic ways that they use to alter the autopilot to damp out or detect and damp out longitudinal phugoid motion, please let me know. With my research and putting my head to that answer, that's what I came up with. If I am wrong, I apologise. You know, but that's my kind of take on that. Okay, that's the answer I would put. Yeah, right. Thanks so much for listening. Comments below. Yeah, and good luck with your final part of assignment 3 if this is part of your Unit 48 study. Thank you. Bye.